Well, I guess we can get started. Welcome back, everyone. So probably the very first thing we ought to talk about is our third exam. And congratulations, folks. That one was really pretty great. It was an unusual exam. I took pretty careful notes on this. Pretty much the entire class was still working well beyond 6:30. So everyone was working at pretty much the same exact pace. And the average came out really great. So I could tell everyone was working really hard. Your hand might have been kind of sore after getting through all that. Sorry about all the writing. But there was a multiple way tie for 100% on this. That's what's driving the average up so much. And it also demonstrates that folks are getting really pretty good at statistical inference and doing those kinds of analysis of interpreting the conclusions that you came up with, identifying parameters. All that stuff is extremely tricky. So congratulations, folks. That was a hard fought exam, I thought, but people did great. Any questions specifically that folks would like to discuss about it? Well, there may not be a ton of questions since folks did really rather well on this exam, but just like the other ones, the solutions are posted here. And you can take a look at that just to see a different interpretation of how I wrote the parameters or the conclusions. I think our work is all pretty similar from what I wrote and what the class wrote. So that's our third exam. All we have left is the final exam to get through. So for the moment, we're getting through section 10.5. That finishes off chapter 10. Then we're going off to chapter 12, and this is our last one. There's just 3 more sections. 12.1 is the extract one. We're looking at a sampling distribution once again. Then 12.2, that's going to be a confidence interval, and 12.3 will be a hypothesis test. It won't be like how we did it in chapter 10 because we will already have seen a hypothesis test. It'll just be a quick change of formulas, but same exact kind of process and interpretation. Also, another thing to mention is I fixed the language on this extra credit opportunity here. We don't have assignments I was referring to. It was more about the quizzes. So I will accept late quizzes. I don't have a specific number. So if you turn in any number of late quizzes, I will accept them. I'm also going to accept quiz do-overs. I mean, the purpose for that is sometimes you learn a lot about a problem after you lose some points, but come back to it after a while and just redo that thing. That's a great way to just solidify knowledge. And if you're redoing a quiz, I just put here, just to be specific, you can just attach your corrections. You don't necessarily have to redo the whole entire thing, unless you want to. Well, that's my announcement so far on this first screen. Any questions or comments at all so far, folks? Okay, let me close this out. We're going to minimize it, actually. So then when we go to next week, there won't be any classes held for the entire week. We'll be probably mostly relaxing. If you're still working though, although I won't have office hours, I'll still be checking my email. Usually I'll only be checking it on the early morning. So that's when I'll be responding. But if you're sending out an email, you don't have to wait for the early morning. Just send it out when you're ready to send out an email. And I'll just get to every one of those messages in the morning. When we come back on this week, that's where we'll be working on 10.5 if there's still a few things to tie up, moving into chapter 12. And that takes us all the way down to the final exam week. So we're getting really close to being completely done. This is going to start populating quite a bit over Thanksgiving break. You'll start seeing specific information. It is a comprehensive exam, but I want to say a little bit more, like what kind of questions to expect, essentially. And also be posting sample exam problems. So same kind of things that as we've been doing all along for exams 1, 2, and 3. So I think that's my whole spiel so far. Any questions or comments whatsoever, folks? Yeah.
Are we getting a quiz for this week?
Oh, thanks for asking about that. I completely forgot that announcement. I did not decide on doing a quiz. I just felt like doing a quiz over the break is just kind of rude after all. And when I've done that historically in the past, almost everyone forgets that there was a quiz. I usually get a lot of lates on that one. So I decided this semester, instead of posting a quiz, I'm just going to do the extra credit opportunity. That way, the folks that have extra time and are eager to continue working on statistics, they'll be available there, but no new quiz this week. Other questions about that so far? Okay, thanks for reminding me about that. That means when we come back to this week, we will have one more quiz here. It'll be due on the week right after, but I can't give a quiz on this week because right after is the final exam. So that week here is going to be a little bit more exceptional. So one more quiz will be posted here, probably something like a confidence interval for a population mean or potentially a hypothesis test. Other questions so far? Okay, well, I think we're ready to get started. So we're now in section 10.5. We're running through a hypothesis test. And we know about how it should go, but in these notes, we're finally putting everything together. And this is what the context was. In a, let's see, year 2000 study, they said 13.6% of 18 to 25-year-olds were current users of marijuana or hashish. I'll just paraphrase that to THC in the problem. They did a new study and found in a sample of 1,283 people, 205 were classified as being current users of THC and in that right age range. So we formalized these hypotheses. The null hypothesis is now just a statement that nothing has changed from the year 2000 to the present day. And the alternative hypothesis has saying we're looking for evidence of a change. We checked conditions, but notice the yellow highlighting here. I won't highlight yellow in the entire notes, this value right here, but example one, the yellow highlighting is specifically because this problem is tricky after confidence intervals especially. Once we state a null hypothesis value, it's used again right down here in condition checking. Let's just make a quick comment here to say, use P naught. By P naught again, we're referring to this value right here in the null hypothesis. So this is our P naught value. Use P naught in condition checking. So we used it twice. We calculated NP naught, got that value, but then we just took the sample size and subtracted the expected number of successes. Then down here, we're expecting P naught when we calculate the test statistic. But this is also very, very surprising. We have to use P naught again right here because now we don't need to make an estimate. If the null hypothesis is true, we put in the exact values right here. So P naught used here for hypothesis testing. Then after putting in those values, we calculate a standard error. Different looking one, but the calculator can't tell the difference. It's the same type of computation. And we found our test statistic was 2.4848. So that would tell us that our statistic of 0.15978 exceeds 2 standard deviations from the hypothesized value of 0.136. Now we want to put down a p-value and say, what does that mean specifically? So that takes us to this current stage. You could look up on the table above on the notes that gives really 4 different cases. A left-tailed test, a two-tailed test, but then, left tail, right tail, and now we're doing a two-tail test from this information here. But then when you do a two-tail test, there's also 2 different cases. If you have a positive test statistic, here's what the picture is going to look like. We'll put a quick normal curve right here. That one's not actually too bad, just a little flat on the top. These are always centered at 0, so the mean is 0, and the standard deviation is always 1 for sigma. And then our z value, let's see, this would be about 1 standard deviations, 2 standard deviations, and maybe that's kind of a hard graph the way I drew it. Let me just go with placing it in a far to the right random location. Here's our z value at 2.4848. Let me shade this. And here's a reminder on this problem. This is a 2-tailed test, but we only highlighted 1 tail. That's just for a little bit of convenience in calculating this. So we will double this area. By this area, we mean that red, I guess that's purple area shaded right there. So finally, our p-value is going to be, here's the doubling, 2 times probability that x is bigger than z. So when we go to calculate this, I'll emphasize the 2 right here. But as long as you get it doubled in the calculator, you have the right expression. So I'll show this as a 2-step process. You may do it as just 1 step. Well, any questions, folks, to this stage? Okay, and I forgot one other thing. This was our process every time we do this. You don't have to write this on your work, but it's always kind of helpful to see in the notes, just in case we get a little bit mixed up. This is input 1 for lower. Input 2 for the upper is going to be positive 10 power 99. Then mu, sigma are inputs 3 and 4. So now it's official. Let's throw this back into the normal CDF calculator. We need to go down to normal CDF and just put in the information in that specific order. So lower is the test statistic, 2.4848. Upper value, 10 power 99, works just fine. Here, mu is 0. Forget which problem we were doing there. And sigma has got to be a 1. Then with that information, here's our almost p-value. This is not quite right. It's 0.00648. But in the calculator, we have to double that. But any questions first to this stage? Okay, let me copy this in as 0.00648. Then double that result. And the calculator, this is all we're doing, just hit times 2 with the answer you just got, so you don't have to worry about copying in all those digits. And that's our actual p-value of 0.012, let's see here, 0.0130 after rounding with Carrie. That's not my favorite rounding problem. 0.0130. Let me double check that. Does that look all right to folks so far on our p-value? Okay, let's take maybe one extra screenshot on this. For these kinds of problems, whenever a 2-tailed test comes up, this is often the most common question. Why is this not being accepted if you gave a 0.00648? And the issue is really just right here in the calculator. We have to do times 2 to get the right p-value. That's not going to show up well. Let's just write it out with a pen. Be sure to double this number in a 2-tailed test. Then we'll have the right p-value finally on this thing. So this is, again, we mentioned last class, it turns out, that some people are strong advocates of a 2-tailed test in every situation. That's a really strong opinion. I don't know if I personally agree with it. The author's textbook does not. But here's where they're probably arguing. If you had this as a right-tailed test, our p-value is much smaller. It looks like we have a much more significant result. But that means we're exposing ourselves to making a type 1 error. If we always do a 2-tailed test, we are making our p-value right here twice as large, which means we need more evidence when we compare against the significance level alpha to reject the null hypothesis. In the sciences, some people advocate that there should be a lot more evidence before we go for a reasonable conclusion. And so some people say, even if you're thinking of testing it as a right-tailed test, do it as a 2-tailed test. Your p-value is twice as large, and now you're going to have more protection against making a type 1 error. But again, that is a very opinionated response there. The reasoning isn't unsound, though. We have doubled our p-value the moment we do a 2-tailed test. So if we're testing for either direction, we're punished in that kind of sense, but it's not necessarily a bad thing. Well, we're just about done with the study. We have to go back to our original context down below and just give a conclusion. Any questions first, folks, before we go for that conclusion now? Okay, before giving it the practical conclusion, this is not a bad thing to put down on your paper. Usually I put it on the same part D, so I'm not saying it's part of the practical conclusion. We're just organizing our thoughts. We take a look at our p-value. It is 0.0130. Then we compare it against our significance level alpha, 0.05. excuse me, since our value here is definitely smaller, we'll go with a less than. This was the value alpha. So this then implies only because we had a less than, we will reject H naught in support of HA. We now have really strong evidence that the alternative hypothesis is true, and we're doing this on a two-tailed test, so that's impressive in a certain sense. All we have to now do is write down that conclusion that we are rejecting the null hypothesis. Visually, there it is, it's scratched out, and we are supporting this, the alternative. Now, we just have to make our overall statement. So it might go, we have found, and this is pretty stylistic the way I'm starting this sentence. You might say, the data provides significant statistical evidence. I'm kind of making it more of an inclusive statement saying, we as a team have found significant evidence. I like to put in statistical evidence, but again, this is more of a stylistic start of the problem. We have found significant statistical evidence that now we have to read out what the parameter is saying. So here's where P is on the alternative. We'll just say that the true proportion or you could say percentage again, true proportion of all 18 to 25-year-olds that are current THC users that will come up here and say is different than 0.136. Is different than 0.136. So we have evidence of a change. Now, if this happened in the study, again, for us as statistical students, the problem really just ends here. This is our whole conclusion. This is only here just to help us set up and write down that practical conclusion. But in a larger study, we would go even further. We would take a look at our data. We have evidence that it's different than 0.136. We would look at, well, what did the sample proportion of successes come out at? It was almost 16%. So we have evidence that it has gone up. And before we say it has gone up, we would have to say by how much. A confidence interval would be given as the next follow-up analysis in a much larger problem. But for us, we're really just going to do the hypothesis test or the confidence interval. But any questions, folks, on getting to that conclusion there? Okay, I want to just add one little extra bit on this. We've been kind of hinting at how a hypothesis test and a confidence interval, they don't exist in isolation. And here is another reason why the two-tailed test is considered a gold standard in a lot of people's minds. Some people say we should never do a left-tailed or a right-tailed test. And here's another reason in support of that. A two-tailed test analysis, like the one we just completed, gives the same exact conclusion as a confidence interval. So in other words, if we did this whole problem as a confidence interval, we would have had a range of values, lower to upper, and we would have found that, yes, the true value is different than 0.136. 0.136 wouldn't have even been in the interval. So a hypothesis test and a confidence interval are really saying the same kinds of things, but with this requirement, provided that the confidence level is take 100%, or let's make this be a decimal. Sorry, let's go with take 1 minus alpha. That might be the better way to say it, since alpha is typically given as a decimal number to start. So the confidence level would have to be 1 minus alpha, which in our problem would have been 1 minus 0.05 equaling 0.95. Or if you prefer percentage, change the unit, and it would be 95%. So we have to keep our confidence level the same as the significance level alpha, in the sense that they both have to add up to 1 exactly right here. If we do that, we're doing the same exact analysis. And then you can say, in a certain real sense, the confidence interval analysis might be better because it gives you more information. Here we're just saying it's different than 0.136. The confidence interval will tell you a whole range of plausible values with 95% confidence that the true proportion P could have been found in. But hypothesis testing still plays its role, and oftentimes, if you're doing a hypothesis test, it goes together with the confidence interval all the same. Well, we did it, folks. That's just the follow-up things to say after doing a hypothesis test, since this is our first full procedure, and to see how it compares with the confidence interval. Any other questions before we go off to try one more? Yeah, go ahead.
So if you're like, even if it gives you something saying that like you should use the right or left tail test,
Yeah,
you can still use the two tail test and it will like come out the same way then?
we should still use the left tail test, or we should use the right tail test in that case.
Okay.
But if it's a two-tail test, it comes out the same as a confidence interval,
Oh,
but only the two-tail test. That's the thing that's kind of unfortunate. If we do a left tail test, our confidence interval might give us a different conclusion than that actual left tail test, which is a bit unfortunate. And same with the right tail test. So still in the problems that we're doing, if they ask for a left tail in some way, we have to provide one. That's what they want for their analysis. The two tails test is still considered the default, and it just happens to give the same analysis as a confidence interval.
so
Does
then-
that help with that question there?
I think so, yeah. So then for the people who were saying like, you should only use two tail tests, then. Like,
That's just their strong opinion, yeah.
so what did they do in that scenario then?
If they had a left tail.
Yeah.
They can change their confidence interval. It's possible, although it looks really weird to do. Let's see if I can Google this. A one-sided confidence interval. So if we're just forced into doing, say, a left tail test, let me see if we can get some good formulas here. And we can, oh geez, that's not what I'm trying to look for. Well, there's a way to reformulate our problems, make a brand new confidence interval where there's going to be just one bound. Oh geez. I was thinking I'd be able to find some actual results somewhere. No one has calculated it from what I can tell. But let me just say, to go along with that comment, for a left tail test, say we're testing HA, that P is less than 0.136, we'd have to dig out those formulas, calculate a confidence interval of the form. It would go like this: negative infinity up to some bound B. And all our confidence interval would say is that B there is the upper bound of the plausible values. So we can, in some way, if we had to, conflate a left tail test with a left-tailed confidence interval, I guess you could call this thing, and same for a right tail test. But that would be a brand new formula, not too many modifications. So I could post those formulas if you're curious about it. And that would allow us to get the same conclusions from left-tailed to that confidence interval, or right-tailed and vice versa. Other questions about that so far? Okay, well, let's try out a brand new problem. This will probably be our last problem for the day, but these are really long problems, so that seems about right. And that means when we come back on our, let's see, Thursday's class, we're probably going to take on example 3 and break into the section 12.1 notes, looking at how to handle numerical data finally. But let's see where this problem right here takes us. Seems like these problems are all about teenagers. I think I got most of these motivated from our author's sample of problems. And looks like she's talking about teenagers when she wrote this chapter. It says in example 2, the paper Teens and Distracted Drivings reported that in a representative sample, so here we don't have a random sample, we're just told it's representative, of 283 American teenagers aged 16 to 17, there were 74 who indicated that they had sent a text message while driving. So it looks like we have a sample size of 283. So those are the teenagers aged 16 to 17, and we have 74 successes. Always makes me uncomfortable to say that's a success when it's not a good outcome. So you can put quotes on that to navigate that moral kind of issue there. Next thing they ask us is, does these data, that's definitely not grammatical. Let's try, do these data provide convincing evidence that more than a quarter of Americans aged 16 to 17 have sent a text message while driving? We'll test an appropriate hypothesis, oh, they gave us something here, using a significance level of 0.01. Always watch out for the significance levels. Sometimes we have to specify our own, like the 0.05 we did in the last problem. But here, we're specifying a 0.01. This is going to minimize a type 1 error, so we're only going to reject the null hypothesis if we have really great level of evidence this time to do so. Well, we're on a great start for this, but there's one value we still need. The value to be tested, P0. And this problem is kind of motivated from what we'll see in WebAssign as well. Sometimes P0 is kind of tricky to find. It's hiding in plain sight, but that doesn't mean it's easy to find. Anyone see where it is or what the value would be? Yeah. Exactly, right where they said here, 1/4. Exactly, absolutely. Let's highlight the more than 1/4 right here. And that's going to imply right tail test. Good eye on that. So let's put in P0 is 0.25 coming from that 1/4. And again, it's kind of awful, but if this ever happens to you, don't hesitate to click on the Ask My Instructor button. Sometimes they really are pretty clever at hiding this kind of information. And if I can find it this time, it doesn't mean I'm going to be great at finding it next time. Sometimes there just feels like a blind spot in getting that information. But we have the P0 at 0.25. I like how you indicated the type of test right here. That's a good strategy to just do that setup. This is a right-tailed test. So after doing all that, it's not a bad idea to read the problem again, then start defining your parameters, your hypothesis test, go through it. But as you're getting through the problem, it might not be bad to come back to the top and just read through it again. Make sure everything we're saying and writing down really is fitting with the context that's being indicated. But after all that preparation, I think we're ready for a parameter. P, I keep on saying parameter, sorry, the population characteristic is our preferred way to indicate this. P will be the true, you could say proportion or percentage. I'll go with proportion of, here I'll say all just to emphasize we're not talking about the sample, we're talking about everybody. But now we have to say who we're meaning when we say everybody. Let's take a look again. The question asks, do these data provide convincing evidence that more than a quarter of Americans aged 16 to 17, so let's say all 16 to 17-year-olds, don't know how many hyphens is expected in that. I'll go 16, let's just say, put a word here, 16 to 17-year-olds. That, what's officially P is the true proportion of successes. So we have to read out what is a success in this problem. But let's go back. We did indicate 74 successes. So go back to that number. There were 74 who indicated that they had sent a text message while driving. I think that deserves highlighting. Let's put in just a gray highlight on that. That's what we called a success when we said there were 74 of them. So we should come back here and say the true proportion of all 16 to 17-year-olds that indicated that they had sent a text while driving. So that's our population characteristic P. Any questions so far, folks, with that parameter here indicated? Okay, now that we have that down, we're ready to put in our hypotheses. H sub 0 or H naught is our null, and it's going to go like this to start. P equals, grab the 0.25 from here and just throw it in. Still feel like highlighting might be helpful here, so I'll just use a light blue highlighting instead of the yellow. Then go to alternative hypothesis, HA. I've been kind of going backwards and forwards. Sometimes I write that as a lowercase a, sometimes an uppercase, but that's all just considered stylistic. So I'll try to stick with one or the other. Here we'll go P compared to the 0.25 again. Then right up here, they're asking for more than a quarter. So we'll test it in this way. More than 25%, or you could put in more than 1/4 or 0.25. But if you do put it in percentage, keep in mind, it really ought to be converted to something else. So we have all that so far. I'll put this here just to make it a little bit more available. And also as a reminder, we want our p-value to be below 0.01 for us to reject this null hypothesis right here and conclude that more than 25% indicated that they have sent a text message while driving. And these kind of statistical problems are really kind of tricky. Even if we make a conclusion, even if we did a confidence interval and provide a huge amount of analysis, it's tricky to know what we really concluded on. Yeah, go ahead.
So that means we want our p-value to be below the 0.01 in order for what?
In order to reject the null and supportive alternative. But what's kind of tricky also about this problem is the word indicated. That's a pretty specific word. They might have used the word omitted instead of indicated, and that would have had the same effect. So in other words, we might not be measuring the actual amount of teenage driving incidents. We're just measuring the amount of people who would admit to driving and texting at the same time. These are very tough problems to get at with absolute truth. So they probably just had to say that in the problem. People may not be honest about behaviors, especially if they're just deemed as shameful by society. It's going to be really, really hard to measure those kinds of things. So let's now go up to part B. But first, any other questions, folks, about our parameter or our hypotheses? Okay, next up is we need to check our conditions. Now, it did say it was a representative sample. That makes me uncomfortable because this is going to take a lot of experts in demographics and maybe dealing with these kinds of issues, DMV experts, to say it really is representative. It was not random. Well, let's say here, we are told we have a representative sample. We might come back to this when we go to write down our conclusion, but that is information we do know about how they collected the data, or rather what they think about once they had all the data together. They feel like this was a representative number of 283 American teenagers, 16 to 17. Next thing we can check is expected, successes, and expected failures. I notice the language that we're writing this out. If it was a confidence interval, we would have said the actual successes in the study. Now, we already know what that is, 74, and we would have said the actual failures in this study. We would have taken 283 minus the 74, but that's not how we check conditions on the hypothesis test. What we have to do is calculate this. We'll take n times p naught to get our expected successes to start. So let's look up our sample size. Up at the top, it's the 283. We multiply that by the value 0.25 from P naught. So we need 25% of 283. One of these teenagers is going to be cut up a little bit. We don't have an exact whole number, but that's okay. 283 times 0.25. We expect these to usually be a decimal number when we do this. And the way to kind of reason our way through this is you could say, if the null hypothesis is really true, and we repeatedly sample 283 teenagers, we would expect this much on average when we take a look at all the possible studies that were concluded. It should be 70.75. But the important thing for us is that this is greater than or equal to 10, so it meets the benchmark for having enough successes. Doesn't mean the sample size is large enough, because we need more than 10 failures, but we automatically can see we're in really good shape. Things go bad if you have too many successes, like say 280 successes would mean there's only 3 failures. And this also goes bad if you have just too few successes as well, less than 10. So expected failures, let's calculate it by taking n minus the 70.75, just calculated. So that's going to be 283 minus 70.75. And so we have a value finally of 283 minus that prior answer gives us 212.25. We exceed 10 here, so we can make a conclusion. This shows the sample size is large enough. We mentioned before when we were first checking conditions with confidence intervals, this is often something that's really easy to miss. We have to make a conclusion, and then we need to make an overall conclusion. We feel like we might be okay if we trust the experts that we have a representative sample and we have a large enough sample size. All this implies the conditions. Let's say this is slightly different. I saw this on one of the papers of the exams just returned, and this is a nice way to make this statement. Let's say overall, the conditions are met. So we're referring to the representative sample and a sample size being large enough when we make that last conclusion right here. So now when we go to write out our conclusion, we'll have some confidence that we're saying the right thing, but I might still come back to this because for me personally, that still makes me kind of uncomfortable. A lot of work has to have gone exactly right for something supposedly a representative sample to truly be representative. But let's go off next down and calculate our test statistic. Again, this gets pretty tricky. We're going to have to call up some information from the problem. We need our sample size of 283. And we're also going to need our null hypothesis as well. So that's a tough screenshot to take. Let me just take it here. Okay, so now it's the test statistic. We'll start by just writing down z equals and put in the formula. It'll be p hat minus p naught. And divide this by standard error of p hat. So that's our formula so far. And let's go with green on that just to match what we did earlier in the notes. There's a definite process once we write down this overall test statistic. Very first thing you'd want to do is definitely calculate p hat. It's used in the other formula for this. Well, excuse me, I misspoke there. That would have made sense for confidence intervals, but it does not make sense for hypothesis tests. P hat does not go inside there. Sorry for misspeaking right there. We'll be really careful when we get to that step. But first for p hat, take in your numerator 74 successes we found, and your denominator sample size of 283. We're going to go for 4 decimal places on our test statistic. So let's take this one to 5 like before. 74 divided by 283. Here's our result. 0.2615. Oh, and let me try again. I have a 0.26148 if I'm going to 5 places. So we've got our statistic here. That's our sample proportion successes. That's kind of a confusing language. The p hat is the statistic, and z is what we're referring to as the test statistic. So let's calculate the denominator of that thing next. For step 2, this is standard error p hat that we know we're calculating. And here's a portion where I misspoke. P hat does not go inside there. You could calculate step 1 or 2 in either order, but I usually like to do the easier step just to get started. What really goes inside there is we're back to the hypothesized value of 0.25. Same value right here from the null hypothesis. So take 0.25, then 1 minus 0.25, and divide this whole thing by sample size of 283. So another computation of this kind, back into the calculator, it'll be second power 2 button for the square root, 0.25 with the open parenthesis, and then 1 minus 0.25, or just throw it at 0.75. Usually I just type it in verbatim, less chance of me making a strange mistake if it's a nastier number. Hit division key, 283. And we have a standard error of 0.02574, rounding to 5 places, 0.02574. Finally, for step 3, after getting p hat value, the standard error value, step 3 is just to plug in the information. So I'll just use the arrow to point towards it. Before we start plugging in the information, any questions, folks, on getting any of those 2 computations in? All right, let's put it all together. We have p hat to start. Go look it up. It's a 0.26148. Subtract, then go to p naught. P naught's value you can always find, well, at the start of the problem if you wrote it down, but also the null hypothesis is the specific place where we find it as well. That's why it's called p sub 0 or p naught, because it comes from the null hypothesis, h naught. So 0.25 will go here. Then the whole result is divided by standard error we just found, 0.02574. At this stage, it's not so bad to throw everything into the calculator. We can now go 0.26148 minus 0.25, divide by, and there's nothing wrong with just typing all this out. That's how we did it on the prior example when we were doing this yesterday. But it's, in fact, more accurate if you up arrow and just type this in. If up arrow doesn't work on your calculator, type in second and the negative sign. Now ANS is referring to the prior answer. It's not only faster, it's not only more accurate, but it's going to help me personally save mistakes, maybe you as well, because I have a bad habit of just keying in numbers wrong. You've probably seen that happen quite a few times over the semester. So here I have more accuracy if I'm using that number. And this comes out as, now to 4 places, 0.4460, rounding with carry. My least favorite kind, but we get good at that after having to do it so many times, I suppose. Now that we have a 0.4460, not a bad idea to make a kind of prediction right at this stage. The thought is it's always a good idea to kind of look before you leap, going to the next problems. And here's what this test statistic is telling us right here. The value of p hat is less than 1 standard deviation away from p naught, which is the 0.25. That means in this problem, we're almost assuredly going to fail to reject the null hypothesis. This isn't very far away in terms of standard deviations. Oh, sorry, Jake, I still have a couple more minutes for this class.
Okay.
But what we still have to do is get the p-value out. Looks like we have, hey, maybe just enough time to make that last step. When we go to calculate the p-value, we compare it against alpha down below here. Any questions first, folks, before we go for the next step, our p-value? Okay, let me go and grab what we'll need for p-value is pretty much just this information right here. We already have the major thing that we needed, which was the test statistic z above. Let me kind of shrink that down. But before we go and write down the p-value, here's the first thought I would want to make immediately on this problem. Take a look at your alternative hypothesis. This is a greater than sign. It's pointing towards the right. And so we're going to say this is a right tailed test. So that means our p-value has this form. It's going to be equal to the probability that x is greater than, only because we said right tailed test, our z value, which was 0.4460 from right above. Then if you like, here's a quick diagram. For actual exam questions, I probably won't tell you to include a graph. It's going to be kind of up to you. Me personally, I probably still would, and a lot of people who do this for a living often just draw pictures. It's a handy way to organize information. This kind of stuff has a pernicious way of just giving the wrong values unless we look at it really closely. So I'm going to put a 0 here. Mean is 0, standard deviation is 1. And the value we're throwing in is z right in this location. Oh, and I put it in a silly spot. 0.4460 really should be pretty close to 0 in this picture. So here's where z is at 0.4460. We go up and shade. That area shaded represents our p-value, and so it represents a really, really large p-value this time. Like before, this value here, 0.4460, that's input 1. Input 2 is 10 power 99. Mu and sigma give us inputs 3 and 4. And so finally, that's pretty much it. To calculate the p-value, we have to know what test we're looking at, so that's why I was looking at this specifically. Draw a quick diagram if necessary, and let's just crank it out. This time we don't have to double any values we get. Whatever we get from this right here, that's our p-value. So back to the calculator once again. Second bars go to normal CDF. There'll always be normal CDF if we're dealing with the p-value. Upper is the test statistic z, 0.4460. I said that weird, sorry. The lower value is 0.4460. The upper value is 10 power 99. The mean is 0, standard deviation is 1. And here's our output. The p-value is large at 0.3278 after rounding. So at this stage, we're just about ready to make a conclusion, but I don't necessarily want to try to write fast as possible. Sorry, folks, it's kind of easy to break these problems in half. Well, let's make a prediction. Based off this value right here, any volunteers for what we'll do? Will we reject the null, or will we fail to reject the null? Yeah, we're in that outcome now. So the p-value is 0.3278. Let's put in a greater than sign, compared against the 0.01, which is equal to alpha. And now, because of that greater sign right there, this is what we don't want. We want a small p-value to have significance, but ours is large. It's larger than alpha. So here we'll say, only because of this, we will fail to reject H naught. So that means we're not supporting H naught. We just didn't find enough evidence to support the alternative hypothesis. And that's a conclusion we'll write when we come back next class. Sorry, it looks like we went right to the minute on that one. Any questions so far, folks? Okay, when we come back next class, that's what we'll do. We'll finish off this study here. And I think we'll try to finish our next example before it gets broken across spring break. That would be terrible. Well, any last questions then at all, folks? Okay, well, have a great night. And this is where we'll be when we come back on Thursday, right before the break.